Welcome to AI Paper Slap. The paper today is 10 Advances in Mathematics and Theoretical Computer Science. And here's the bottom line for you. An internal, unreleased version of the AI model Astra just solved 10 major open problems in math and theoretical computer science.
Yeah, and these are problems that haven't seen like a single drop of progress in over a decade.
Right. If you look at the screen right now, you're seeing the title of the paper, and right below it, a list of these 10 breakthroughs. We are talking about everything from classical math all the way to quantum complexity.
It's just wild.
It really is. And the AI did the actual thinking for roughly $2,000 at sole API rates, which, I mean, is nothing. And the proofs have been formally verified in Lean. So our mission for this deep dive, we're going to walk through how this model actually achieved these breakthroughs, break down the 10 specific advances, and, discuss what this means for the future of human AI research collaboration.
It really is a profound moment for the field. I mean, when you look at that list on the screen, you aren't seeing the typical incremental progress, right? You're seeing a system systematically break through these structural brick walls.
Okay, let's unpack this a bit, because before we get into the really dense math, we need to understand the mechanics of how these results were actually generated.
Yeah, the methodology is crucial here.
Because I read the methodology section, and I have to admit, it raised a flag for me. The paper specifically notes that humans prepared the manuscripts using the model.
Right, the human element is still there.
Yeah, so if this Astra model is as incredibly smart as the results suggest, why did humans even need to step in to write it up? It's kind of like having this hyper-genius oracle that spits out raw, brilliant logic, but you still need a human translator to, format it for the scientific community.
What's fascinating here is the exact pipeline they used, because it fundamentally changes how we should view discovery. If you look at the flowchart we're putting up on the screen right now, you'll see this distinct AI to human to lean workflow.
Okay, yeah, I see it.
So first, the internal Astra model generated the arguments. That's the raw reasoning part that cost like $2,000 in compute.
Which is just a staggering number when you think about the grants usually required for this.
Exactly, millions of dollars and thousands of human hours normally. But the model's raw output isn't a finished paper. The human researchers had to step in as curators. They took those raw insights and used the exact same model to format them into standard academic prose.
Which I guess brings up the obvious skepticism from, anyone working in ML. How do we know the reasoning is actually sound and not just incredibly convincing pattern matching?
And that is exactly where the third step comes in.
Right, the lean verification.
Yeah. The ultimate safety net here is that the model formalized each of its own arguments into a Lean certificate to prove its absolute correctness. For the ML engineers watching, Lean is a formalized theorem prover.
It's basically a functional programming language, right?
Right, where proofs are programs and theorems are types. You cannot handwave in Lean. A human might write, it trivially follows that, but Lean forces you to rigorously compile every step down to the fundamental axioms.
So it bridges the gap between like an intuitive neural network leap and deterministic verification.
Exactly. And the authors are even releasing the model's narration of its thinking process, which we'll get to later, but it's huge.
Okay, so let's transition from the engine to the actual victories, starting with the first 4 problems. We're moving from spatial reasoning to abstract algebra.
The geometry and codes section.
Yeah. The first major milestone here is high-dimensional sphere packing. Astra found new upper bounds and went all the way down to the Cohen-Elkys threshold.
Which is a massive deal. Sphere packing basically asks, how densely can you pack identical spheres into a given space? Like grocer stacking oranges, but in hundreds of dimensions.
Right, mathematicians just have to make it complicated.
Always. But the Cohen-Elkys threshold is this theoretical ceiling. We've known it exists for years, but proving bounds that tightly hug that threshold in specific high dimensions has been practically impossible until Astra.
And then it connected this to information theory, right? It achieved exponentially improved bounds on the maximum sizes of binary and spherical codes at prescribed minimum distances.
Yeah, which is huge for data transmission.
For our audience, just to clarify, sphere packing and error-correcting codes are essentially the same mathematical problem, just wearing different trench coats, right?
That is a perfect way to put it, yeah. When you transmit data over a noisy channel, like a deep space probe sending telemetry, you encode it into binary strings. You want to pack as many valid code words into that space as possible to transmit lots of data.
But you have to keep them far enough apart so a burst of static doesn't corrupt the message.
Exactly. That's the minimum distance. The bounds on how efficiently you can pack these codes have been stuck for decades. Astra provided exponential improvements here.
Wow. But here's where it gets really interesting for me. It shifted into pure abstract group theory. Problem 3 and 4. Astra constructed non-sofic groups, proving their existence.
Yeah.
But more importantly, it disproved Kahn's rigidity conjecture. It literally disproved the idea that certain groups are uniquely determined by their von Neumann algebras. That is wild to me. It's not just proving human ideas right, it's actively finding the blind spots in our intuition.
Disproving a conjecture is just an entirely different beast. When you prove something, you're usually building a bridge using known architectural principles. You kind of know where you need to go.
But disproving it means you have to find a structural flaw everyone else missed.
Right. It requires finding a counterexample in these incredibly dense operator algebras. It proves the model can navigate complex abstract spaces, not just crunch numbers.
It's not bound by our aesthetic biases where we expect symmetry and elegance. It just sees the math.
Exactly. It found the asymmetric edge cases we assumed didn't exist.
Okay, so moving on to the next batch, problems 5 through 7. This takes us from pure mathematics into theoretical computer science, complexity and cryptography.
This is where it gets really practical for computer scientists.
Definitely. It tackled arithmetic circuit complexity, finding a new lower bound. We're showing the arithmetic formula right now on the screen. It's n to the fourth over log n, specifically for computing the permanent of a matrix.
If we connect this to the bigger picture, establishing a lower bound is notoriously difficult. It's basically trying to prove a negative.
Right, because proving an upper bound just means you write an algorithm. If I write a script that runs in n squared time, boom, upper bound is at least n squared.
Exactly. But a lower bound means guaranteeing mathematically that no algorithm in the history of the universe can ever solve it faster than that speed.
You have to rule out every hypothetical shortcut.
Yeah, and the permanent of a matrix is this classic, famously difficult problem. By proving this lower bound, Astra is fundamentally advancing the theoretical limits of what classical computers can actually do.
And it didn't stop at classical computers. It proved an exponential parallel repetition theorem for general two-player quantum games.
Which is a huge relief for cryptography.
Right, because classically, parallel repetition is how we amplify security. You make a hacker solve a puzzle 50 times, their chance of winning drops exponentially. But in the quantum realm, entanglement kind of breaks that logic, doesn't it?
It does. Quantum players can share entangled qubits to correlate their answers without physically communicating.
Which is just spooky.
It is. And the fear was that this entanglement might let them bypass that exponential decay entirely. But Astra proved that even with general quantum strategies, the probability of winning still decays exponentially.
Oh, wow. And that ties perfectly into problem 7. The closest vector problem, or CVP. Astra proved the polynomial factor hardness of approximation here.
Right, which relates directly to post-quantum cryptography.
Yeah, I want the listener to really look at the visual representation of a multidimensional lattice we have on the screen right now.
Because lattices are everything right now in security. Traditional encryption, like RSA, will be broken by quantum computers using Shor's algorithm.
So the whole world is migrating to lattice-based crypto.
Exactly. And in a lattice, which is like a repeating grid of points stretched across hundreds of dimensions, finding the closest lattice point to an arbitrary spot is insanely hard.
It's like trying to find one specific star in a dense galaxy while your perspective just keeps shifting.
Yeah, and Astra proving this hardness of approximation for CVP provides the rigorous bedrock we need. It proves why these lattice systems will stay secure against future quantum attacks.
Okay, so it fortifies the future internet, and then it just pivots to extremal combinatorics for the last 3 problems, specifically problems posed by the legendary Paul Erdos.
The ghost of Erdos, yeah.
I have to remind the listener of some context here. Back in May, an unreleased model had already disproved the Erdos unit distance conjecture. Now, Astra takes down 3 more Erdos problems. It honestly seems like Astra has a personal vendetta against his unsolved list.
It's funny, but it makes sense as a benchmark. Erdos problems in extremal combinatorics require finding absolute limits within networks and graphs.
Right, like Earhart's volume conjecture. Astra determined the max volume of a convex body in every dimension where the centroid is the only interior lattice point.
It's a beautiful geometry problem, but the Ramsey theory result, problem 9, is what really blew me away.
Resolving Erdos problem 183, it found a center exponential lower bound for multicolor Ramsey numbers.
Right. Ramsey theory is basically the study of order inevitably emerging from chaos. Like, how many people do you need at a party to guarantee 3 are mutual friends or mutual strangers?
But as you add more colors, like more types of relationships, the network size required to guarantee patterns just violently explodes, doesn't it?
It explodes into practically incomputable territory. And finding a super exponential lower bound means Astra proved this network grows faster than any standard exponential function.
It's just systematically decoding fields that used to rely entirely on heavy human intuition. And it wrapped it all up by resolving the compactness and degeneracy conjectures, hitting Erdos problems 146 and 180.
It's staggering.
So what does this all mean? We have to step back here. How is the community supposed to adapt when a $2,000 API call can do what used to take an entire human career?
This raises an important question, and it's one the authors tackle in the paper when discussing the Leiden Declaration on AI and mathematics.
Right, the ethical side of this.
Yeah. The authors argue that AI shouldn't be given human-style authorship. It misrepresents genuine human intellectual work.
Even though the AI did the heavy lifting for the actual logic.
Exactly. The human researchers take responsibility for the correctness, they verify it, but they acknowledge the arguments are undeniably the system's.
Which explains the rollout of the ChatGPT for Academic Researchers program they mentioned, giving 100,000 scientists free access. You can't just have a few labs hoarding this oracle while everyone else chips away manually.
Right. It's about leveling the playing field.
It really is. So, to synthesize this,
Right.
from sphere packing to quantum games, the landscape of theoretical research has just permanently shifted.
It's a completely new era.
But before we sign off, I know you wanted to leave the listener with a final thought about the source material.
Yeah, I do. Because the authors released the model's narration of its thinking process for every single solution. Not just the lien certificates, but the actual step-by-step reasoning tokens.
Right.
As researchers, we shouldn't just look at the certificates to see that the math is right. We need to study these narrations. If an AI can solve a decade-old problem in a few tokens, is its thinking process structurally alien to human logic?
Or is it just human logic executed flawlessly without our memory bottlenecks?
Exactly. Are we about to learn a completely new way to reason?
That is the big question. Well, I highly encourage you all to read the full narrations for yourselves. Thank you for joining us for this deep dive on AI paper slop, and we'll catch you next time.